You take the piston and draw the piston outside. So this is the piston stroke. When you make that piston stroke, how much is the volume accommodated? What is this volume equal to? That's what is this delta V. Your gas can now expand and reach this volume as well. The same gas goes into that. So now, if you take the gas which was there in the vessel has now gone outside into that piston, as if it was there in the room first and now it has gone to the balcony. So the pressure initially, if you take as P naught, and we can employ the Boyle's law here. What is the pressure now? Because this gas has expanded to the same volume has become a bigger volume. The bigger volume is V plus delta V. This pressure has become, let us say, P1. So after the first piston stroke, the pressure has reduced to P1. It is the same mass of the gas. Now what you do is, there will be some mechanism by which you can close this off. If you close this off, now this much gas is taken out. We close this. What is the pressure here now? That's P1. And you can throw out this gas, empty that gas outside, and repeat procedure. You empty this gas outside. This is gone now. After one stroke, the pressure has become P1. Now again you will inject that piston and again draw the gas. So the piston will be here and then you will draw the gas. When you draw the gas, this time, initially the pressure was P1, now the pressure will become P2. Repeat procedure. So this goes on like that. So what will happen? After the nth stroke pressure will be Pn into V plus delta V, whereas prior to that it will be Pn minus 1 times V. Each time we are applying the Boyle's law for a given mass of a gas. The mass of the gas remains constant as long as gas goes from here to there. Afterwards it's a new question when you repeat the cycle. So can we now solve this? If you just multiply everything from top to bottom, P1 cancels off with P1, this P2 will cancel off with this P2, Pn minus 1 will cancel off with the Pn minus 1 here. So what do we get when you multiply? So you will get P naught V n times, and you get Pn V plus delta V n times, power n. And you are saying that pressure should go down by eta times. That means this final pressure should be P naught by eta. Solve for n, that's your answer. So what do you get n equal to? You can take a log and solve it, no? N equals how much? Take log on both sides and simplify. Yeah, how much you getting?
Log of eta upon log of E plus delta V upon V.
Log eta by log of 1 plus delta V by V. That's the required answer. Yeah, is that fine?
Yes.
Sir?
Yeah.
Sir, I read it by a different method, so can you tell the error? Sir, I read it that...
Who is speaking? Could you raise your hands, please? I'm not able to make out. Yeah, say.
Sir, PV is equals to nRT.
Just a minute. Yeah, you are saying PV equals nRT, then?
Sir, then if we differentiate both the sides,
Yeah.
sir, we get P delta V is equals to minus V delta P.
Differentiate with respect to this differential will be PdV, but your temperature is constant, so PdV plus VdV is 0. Yeah.
Sir, now dV is N times dV.
dV is?
Sir, N times dV. We can't do
See,
that.
no. This is not the same gas. Every time the gas is changing. You take one part of the gas, then you remove some gas. Then that second gas is a different section of a gas. Then you remove it. It is not the same gas. I have put Boyle's law separately for each one of the gases. It is not if it is not the same gas, then how can you do it? Every time you take the gas, then throw it out. And then again you inject the piston, throw it out. So it is not the same thing to begin with. So what are you differentiating? the function is not continuous, differentiation will not hold. Rather, since you asked me the differentiation part, let me give a part 2 of this question. B part to this question. Take it. If the evacuation rate is C, what is P as a function of time? You can assume the initial pressure as P naught. Here, if you check it out in terms of a small time dt, in a small time dt, the piston will suck out. Now there is some mechanism by which there is a continuous sucking of volume. So let us talk about a small time dt. So in a small time dt, initially the pressure volume is P into V. But in a small time dt, what happens? This would occupy a certain volume which we'll call as C dt, because that is the evacuation. C is the evacuation rate. So the volume taken in is C dt, and the pressure will change by dP. The volume will become V plus C dt. We can use this as a Boyle's law between T and T plus dt timings. This is the time T, this is the time T plus dt, this is the Boyle's law. That gas which was there in that vessel has slightly gone to the evacuation pump. So now this is the differential equation which we can create. What is the differential equation we get? PV equals PV plus PC dt plus VdP plus dP C dt. Now PV cancel. dP into dt is infinitesimal and infinitesimal negligible, tending to 0. We drop this. So what do you get? You get VdP equals minus PC dt. In other words, you get dP by P equals minus C by V times dt. Differential equation you have got, which you can integrate now. At 0 time, the pressure is P naught. At time t, the pressure is P, and that is the required answer. Guys, that's fine. We'll get that as the answer.